The universe is approximately 93 billion light-years in diameter. That measurement represents the observable portion, the sphere of space from which light has had time to reach us since the Big Bang. Beyond that boundary lies more universe, stretching outward in every direction. How much more? Nobody knows. The answer might be infinite. It might be a number so staggeringly large that infinity becomes a simpler concept to grasp than the actual figure. James Webb Space Telescope began operations in July 2022. Within months, it detected galaxies that shouldn't exist. These weren't just distant galaxies, they were massive, fully formed spiral galaxies existing merely 300 to 400 million years after the Big Bang. According to our models of cosmic evolution, such structures required billions of years to assemble. The universe hadn't provided enough time. Yet there they were, rotating serenely in the primordial darkness, their light stretched across more than 13 billion years of cosmic expansion before reaching the telescope's gold-plated beryllium mirrors. The discovery forced astronomers to reconsider everything they thought they understood about cosmic scale. Not the size of the observable universe, which remains fixed by the speed of light and the age of the cosmos. Something deeper. The sheer magnitude of structure that can form within cosmic timescales. The volume of space that participates in organized patterns. The extent to which gravity can sculpt emptiness into architecture. This is about scale in a different sense. The scale of cosmic possibility. The scale of what the universe can accomplish. The scale of our ignorance regarding what lies in the darkness beyond our instruments. Think about what happens when you look at the night sky. Your eyes collect photons. Each photon traveled for years, centuries, or millennia before entering your retina. The furthest objects visible to the naked eye are galaxies millions of light years away. Their light departed before humans existed. You're seeing ancient history, the past made visible through electromagnetic radiation. Telescopes extend this reach. The Hubble Space Telescope, launched in 1990, could detect galaxies from when the universe was roughly 500 million years old. James Webb, with its 6.5-meter primary mirror and infrared sensors cooled to minus 233 degrees Celsius, peers even further back. It observes wavelengths of light that have been stretched by cosmic expansion from visible and ultraviolet into the infrared spectrum. Light that began its journey as blue or white now arrives as invisible infrared, shifted toward longer wavelengths by the expansion of space itself during the photon's multi-billion-year transit. This expansion creates something counterintuitive. The galaxies James Webb observes at 13.4 billion light-years distance are no longer at that location. They've been carried away by expanding space. Today, accounting for 13.4 billion years of cosmic expansion, those same galaxies now reside roughly 46 billion light-years away. We observe their ancient past, but their present location has receded far beyond the reach of any signal we could send. The light we see departed when the universe was young. The galaxy that emitted it has aged, evolved, perhaps merged with neighbors, or been torn apart by gravitational interactions. We cannot know. Their current state remains hidden behind the cosmic horizon, separated from us by distance and by time itself. Here's where the numbers become truly uncomfortable. The observable universe extends 46 billion light-years in every direction from Earth. That's 93 billion light-years in diameter. The volume of a sphere that size contains roughly 2 trillion galaxies, each home to an average of 100 billion to 400 billion stars. Multiply those numbers. The observable universe contains approximately 200 billion trillion stars. That's 200,000 individual fusion reactors, each converting mass to energy according to Einstein's equation. Most of those stars host planets. Recent surveys by the Kepler Space Telescope suggest nearly every star in the Milky Way has at least one planet. Extrapolate that finding across 2 trillion galaxies, and the number of planets in the observable universe reaches scales that dwarf even the stellar count. But the observable universe is not the universe. It's merely the portion from which light has had time to reach us. Beyond that boundary lies more space, more galaxies, more structure. How much more? This is where measurements become impossible and logic takes over. The universe is either finite or infinite. If finite, it must have a shape, an edge, a total volume. If infinite, it extends forever in all directions, containing infinite matter, infinite galaxies, infinite copies of you reading these words in infinite variations. Current measurements suggest the universe might be flat, not flat like a pancake, flat in geometric terms, meaning parallel lines remain parallel forever. Triangles contain exactly 180 degrees, and space continues outward without curving back on itself. Teams measuring the cosmic microwave background using the Planck satellite determined that the universe's curvature parameter omega sub k equals 0 within measurement uncertainty, roughly plus or minus 0.004. A flat universe extends infinitely. Space doesn't curve around to meet itself. It simply continues, without boundary, without end. Calculate what that means. An infinite universe contains infinite galaxies, infinite stars, infinite planets. The laws of probability applied to infinite space produce every possible arrangement of matter. Somewhere in that infinite expanse exists another Earth, identical to ours down to the atomic level. Somewhere else exists an Earth where you made different choices. The configurations repeat because infinity demands it. Given infinite space and finite possible arrangements within any given volume, every pattern must occur not once, but infinitely many times. The evidence for flatness comes from detailed measurements of the cosmic microwave background. This radiation fills all of space, a faint afterglow of the Big Bang cooled by expansion to just 2.725 Kelvin above absolute zero. The temperature varies by tiny amounts, roughly 100 microkelvins, creating a pattern of hot and cold spots across the sky. These spots correspond to density variations in the early universe, regions slightly denser or less dense than average. Gravity amplified those variations over billions of years, transforming them into the cosmic web of galaxies, clusters, and voids we observe today. The size of the spots encodes information about cosmic geometry. In a flat universe, the spots appear a certain angular size. In a curved universe, they would appear larger or smaller, magnified or diminished by the bending of space. Measurements by the Wilkinson Microwave Anisotropy Probe in 2003 and refined by Planck in 2013 and 2018 consistently show the spots at exactly the size predicted for flat geometry. The universe doesn't curve, it extends. But here's the troubling detail that James Webb has forced cosmologists to confront. Even if the universe is flat and infinite, the scale of structure formation exceeds theoretical predictions. Those early massive galaxies represent merely one piece of a larger puzzle. Webb has also detected supermassive black holes existing at cosmic dawn, objects containing millions of solar masses when the universe was less than 500 million years old. Black holes of this size should require hundreds of millions or billions of years to accumulate their mass through gradual accretion of surrounding gas and smaller black holes. The universe hadn't provided enough time. Yet they exist. their gravitational fields bending the light of even more distant galaxies behind them, creating Einstein rings and distorted arcs that betray the presence of extreme gravity. Something about our models of structure formation is wrong. Either matter clustered together faster than simulations predict, or the initial conditions in the early universe were more complex than we assumed. Perhaps the density variations in the primordial universe were larger than the cosmic microwave background suggests. Perhaps dark matter interacts with itself in ways that accelerate galaxy formation. Perhaps the first stars were far more massive than current models allow, burning through their fuel in mere millions of years and collapsing into black holes that quickly merged into supermassive giants. The implications reach beyond galaxy formation. If structure developed faster than expected, the universe might be more organized, more thoroughly processed, more completely evolved than we realized. The regions we observe through our telescopes might represent a universe that has already reached structural maturity, with most of the gravitational architecture already in place even at early times. This creates a problem for cosmological surveys attempting to map the large-scale structure of the universe. Astronomers have spent decades cataloging galaxies, measuring their positions and distances, constructing three-dimensional maps of cosmic structure extending billions of light-years from Earth. These surveys revealed the cosmic web, a vast network of galaxy filaments separated by enormous voids. The filaments stretch for hundreds of millions of light-years, containing thousands of galaxies gravitationally bound into superclusters and clusters. The voids contain few galaxies, appearing as dark bubbles in the cosmic foam. The Sloan Digital Sky Survey, which began operations in 2000 and continues today, has mapped the positions of more than 3 million galaxies. The resulting structure shows clear patterns. Galaxies cluster along filaments. The filaments intersect at massive galaxy clusters containing thousands of individual galaxies. The voids push outward, growing larger as cosmic expansion stretches space and gravity continues to pull matter from underdense regions into denser filaments. But James Webb's discoveries suggest this structure formed earlier than models predict. If massive galaxies existed 300 million years after the Big Bang, the seeds of the cosmic web must have been planted even earlier, in the first moments after the universe became transparent to light. The density variations measured in the cosmic microwave background trace back to quantum fluctuations during inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. Those microscopic quantum jitters were stretched to cosmic scales, creating the blueprint for all subsequent structure. The jitters shouldn't produce massive galaxies as early as Webb observes them. Standard cosmology predicts a gradual buildup of structure. Small, dark matter halos form first, collecting gas that cools and forms stars. These protogalaxies merge, building larger structures over hundreds of millions of years. The process should produce small, irregular galaxies first, with large spiral and elliptical galaxies appearing later, after sufficient time for mergers and growth. Webb sees the opposite. Massive galaxies appear fully formed at cosmic dawn. Spiral structure exists when the universe was barely 500 million years old. The Hubble sequence of galaxy types, developed by Edwin Hubble in 1926 to classify galaxies by their shapes, appears to apply even in the earliest epochs. Elliptical galaxies, spiral galaxies, barred spirals all exist in James Webb's deep field images of the primordial universe. Think about that for a moment. The morphological diversity of galaxies emerged not gradually but immediately. The universe wasted no time experimenting with different structures. From the moment gravity could assemble matter into galactic-scale objects, it produced the full range of forms we see in the local universe today. Either the assembly process operates on faster timescales than we understand, Or the early universe possessed properties that accelerated structure formation in ways our simulations don't capture? One possibility involves dark matter. This invisible substance comprises roughly 85% of all matter in the universe. It doesn't emit, absorb, or reflect light. It interacts only through gravity, pulling on normal matter and on itself. Dark matter provided the gravitational scaffolding upon which galaxies formed. Simulations showed dark matter clustering first, creating gravitational wells into which normal matter fell, collecting into dense clouds that eventually ignited stars. But dark matter remains mysterious. We've never directly detected a dark matter particle. We infer its existence from gravitational effects, from the rotation curves of galaxies that spin too fast for their visible matter alone to hold them together, from the gravitational lensing of distant galaxies by foreground galaxy clusters, from the pattern of fluctuations in the cosmic microwave background. All evidence points to vast quantities of invisible mass permeating the cosmos. What that mass consists of remains unknown. Candidates include weakly interacting massive particles, or WIMPs, hypothetical particles that interact via gravity and the weak nuclear force, but pass through ordinary matter almost completely undetected. Experiments deep underground and at particle accelerators have searched for WIMPs for decades. None have been found. Axions represent another candidate. Ultralight particles propose to solve problems in quantum chromodynamics. Primordial black holes, formed in the intense conditions of the early universe, could also account for some or all dark matter. Each candidate predicts different behavior for structure formation. What James Webb has revealed suggests dark matter behaved in more complex ways than standard models assume. Perhaps dark matter particles interact with each other through forces we haven't characterized. Perhaps the density of dark matter in the early universe varied more dramatically than the cosmic microwave background indicates. Perhaps dark matter clustered more efficiently than simulations predict, forming the seeds of massive galaxies earlier than our models allow. Alternatively, the problem might lie not with dark matter, but with our understanding of the initial conditions. The cosmic microwave background shows us the universe at 380,000 years after the Big Bang, the moment when the universe cooled enough for atoms to form and light to travel freely through space. Before that moment, the universe was opaque, filled with a hot plasma of ions and electrons that scattered photons. We cannot directly observe the universe before 380,000 years. We must infer earlier conditions from theoretical models and from the pattern imprinted in the cosmic microwave background. Those models might be incomplete. The inflationary epoch that preceded the formation of the cosmic microwave background remains poorly understood. Inflation theory proposes that the universe underwent exponential expansion in the first fraction of a second, driven by a scalar field called the inflaton. This expansion stretched tiny quantum fluctuations to cosmic scales, creating the density variations that eventually became galaxies. But the details of inflation remain unclear. What was the inflaton? How long did inflation last? Did it end everywhere simultaneously? Or did different regions of space stop inflating at different times, creating a patchwork of bubble universes with different properties? Different models of inflation predict different levels of initial density variation. Perhaps the quantum fluctuations during inflation were more vigorous than standard models suggest, creating larger density peaks that could collapse into massive structures more quickly. Perhaps inflation didn't homogenize the universe as thoroughly as we thought, leaving behind regional variations in density or in the properties of dark matter that accelerated structure formation in specific areas. James Webb's observations provide clues. The massive galaxies it detects aren't randomly scattered across the sky. They appear in specific regions, suggesting that structure formation wasn't uniform. Some areas of the early universe produced massive galaxies quickly. Other areas remained relatively empty, with structure developing more gradually. The pattern hints at underlying variations in the initial conditions, regions where the density of matter or dark matter was unusually high, allowing rapid collapse into gravitational structures. But there's something else happening, something that makes the scale of the universe even more impossible to grasp. James Webb doesn't just see distant galaxies, it sees them gravitationally lensed by foreground structures, their light bent and magnified by the gravity of massive galaxy clusters lying between us and the distant source. These lensing clusters act as natural telescopes, amplifying the light of objects that would otherwise be too faint to detect. The most powerful lensing events magnify background galaxies by factors of 10, 50, or even 100, turning objects that would appear as faint smudges into detailed structures whose spiral arms and star-forming regions become visible. This gravitational lensing allows James Webb to peer even further back in time, detecting galaxies that existed just 200 million years after the Big Bang. These objects, designated by their redshift values of Z equals 12, 13, or even higher, represent the universe in its infancy. Their light has traveled for more than 13.6 billion years, redshifted by cosmic expansion until originally ultraviolet light arrives as mid-infrared radiation. James Webb's sensors detect photons at wavelengths of 3 to 5 microns, nearly 10 times the wavelength at which they were emitted. The galaxies themselves are small, merely a few thousand light-years across, but they contain millions or billions of stars already. Star formation proceeded incredibly rapidly. Gas clouds collapsed under gravity, fragmented into dense cores, and ignited fusion in timescales of millions of years, rather than the tens or hundreds of millions of years typical of later epochs. The first stars, called population 3 stars, might have been far more massive than stars forming today, reaching hundreds of solar masses and burning through their fuel in just a few million years before exploding as supernovae or collapsing directly into black holes. These massive stars enriched the early universe with heavy elements: carbon, oxygen, silicon, iron, the products of nuclear fusion in stellar cores. When the stars exploded, they scattered these elements into the surrounding gas, where they cooled and condensed into the next generation of stars. Each stellar generation increased the metallicity of the universe, the fraction of matter composed of elements heavier than hydrogen and helium. James Webb can measure this metallicity by analyzing the spectra of distant galaxies, looking for absorption and emission lines from specific elements. The observations reveal surprisingly high metallicity, even in galaxies from just 300 to 400 million years after the Big Bang. These galaxies already contain significant quantities of carbon and oxygen, suggesting multiple generations of stars had already lived and died. The universe recycled matter quickly, processing primordial hydrogen and helium through stellar furnaces and distributing the products throughout space. This rapid chemical evolution connects to the question of cosmic scale in a profound way. If the universe processed matter this efficiently everywhere, then the volume of space containing heavy elements expands dramatically. Planets require heavy elements: carbon, oxygen, silicon, magnesium, iron. These elements form the rocky planets on which life as we know it can develop. If the universe produced these elements quickly and distributed them widely, then the conditions necessary for planets and potentially for life appeared much earlier than previously thought. Calculate the implications. If habitable planets could form when the universe was 500 million years old, and if life emerged quickly on some fraction of those planets, then the universe might have hosted living worlds for more than 13 billion years. Civilizations could have risen and fallen while our corner of space remained lifeless hydrogen gas. Technologies could have developed, matured, and perhaps transcended physical form entirely billions of years before Earth coalesced from the solar nebula. This is speculation, but it's speculation rooted in observation. James Webb has shown us that the universe assembled structure far more rapidly than we expected. Structure enables complexity. Complexity permits life. The timeline for biological and technological evolution might be far longer than the 13.8 billion years between the Big Bang and now. It might encompass multiple epochs of cosmic history, with life emerging, spreading, and evolving across billions of years, while the universe expanded, cooled, and transformed around it. Yet we see no evidence of these ancient civilizations. The sky is dark. The radio spectrum is quiet. Optical surveys detect no megastructures, no Dyson spheres, no engineered artifacts on galactic scales. This is Fermi's paradox, formulated by physicist Enrico Fermi in 1950. If the universe is vast, ancient, and rapidly filled with the building blocks of life, where is everybody? James Webb's discoveries make the paradox more acute. Not only is the universe larger and older than we are, but it became capable of supporting complex chemistry and potentially life far earlier than previous models suggested. The window for intelligence to emerge and spread stretches back billions of additional years. Yet the silence remains unbroken. Several explanations present themselves. Perhaps life is extraordinarily rare, requiring such specific conditions that even across 2 trillion galaxies and billions of years, intelligent technological civilizations remain sparse, separated by distances and times so vast that communication or travel between them is effectively impossible. Perhaps civilizations inevitably destroy themselves or stagnate before achieving the capability to signal across interstellar or intergalactic distances. Perhaps intelligence is common, but technology takes forms we don't recognize, operating in domains of physics we haven't accessed, or communicating through channels we can't detect. Or perhaps the universe is even larger than we've imagined, and the scale alone makes contact impossible. An infinite universe contains infinite civilizations, but infinity also contains infinite distance. The nearest technological civilization might be separated from us not by thousands or millions of light years, but by billions, residing in a galaxy so distant that its light hasn't yet reached Earth, or that has been redshifted beyond detectability by the expansion of space. This brings us back to the question of cosmic scale and to what James Webb has truly revealed. The telescope hasn't measured the size of the universe. That remains unknowable, potentially infinite. What Webb has measured is the scale of cosmic structure, the distances over which gravity has organized matter into patterns, the volume of space that participates in the architecture of galaxies, clusters, and voids. And that scale is immense, far more immense than our models predicted. The universe didn't gradually build structure over billions of years. It jumped immediately into large-scale organization, assembling massive galaxies and supermassive black holes in the first few 100 million years. The implications suggest that the laws of physics favor structure formation, that gravity operates efficiently across vast volumes of space, pulling matter together into dense concentrations despite the expansion of the universe, trying to pull everything apart. This tension between expansion and gravitational collapse defines cosmic evolution. The Big Bang set space expanding. Gravity tries to pull it back together. Which force wins depends on the density of matter and on the presence of dark energy, a mysterious component that accelerates cosmic expansion. Measurements indicate that dark energy comprises roughly 68% of the total energy density of the universe, with dark matter contributing 27% and normal matter just 5%. Dark energy produces a repulsive force that increases as space expands. More space means more dark energy, which accelerates expansion further, creating even more space in a runaway process. Eventually, billions of years in the future, dark energy will dominate completely. Cosmic expansion will accelerate to the point where even gravitationally bound structures begin to tear apart. Galaxy clusters will disperse. Galaxies themselves might dissolve. Stars will be separated from each other by ever-increasing distances until each star becomes an isolated island in an expanding void. But that fate lies trillions of years ahead. For now, in the current epoch, roughly 13.8 billion years after the Big Bang, gravity and expansion exist in balance. Structure has formed. Galaxies cluster. Stars ignite. Planets orbit. Life emerges, at least here on Earth and perhaps elsewhere in the cosmos. James Webb observes this balance playing out across cosmic history. The massive galaxies it detects at cosmic dawn represent gravity-winning local battles against expansion, pulling matter together despite the universe's overall tendency to dilute and spread. These gravitational victories created the structures we see today, the galaxies and clusters that populate the cosmic web. But expansion is winning the larger war. The universe continues to grow. Distances between galaxy clusters increase. Eventually, clusters will recede beyond the cosmic horizon, carried by expanding space to distances where light can never bridge the gap. Future astronomers billions of years hence, if any exist, will observe a lonelier universe than we do, with fewer galaxies visible in their skies, the most distant structures having receded beyond the reach of detection. We exist at a privileged moment in cosmic history, late enough for structures to have formed and for complexity to have emerged, but early enough that the universe remains visible, filled with galaxies whose light can still reach us. James Webb captures this moment, imaging the cosmos at the peak of its richness, before dark energy's acceleration carries most of the universe beyond our cosmic horizon. The telescope's observations also reveal something else about cosmic scale, something that relates to the nature of space itself. Light from distant galaxies has traveled through expanding space for billions of years. During that journey, the wavelength of the light stretched along with space. This cosmological redshift provides a direct measurement of how much the universe has expanded since the light was emitted. A galaxy observed at redshift z equals 2 emitted its light when the universe was roughly 1/3 its current size. Every distance in the universe was 3 times smaller. Galaxies were 3 times closer together. The cosmic microwave background was 3 times hotter. Dark energy was less dominant, and matter and radiation played larger roles in cosmic dynamics. A galaxy at redshift z equals 10, near the limit of James Webb's detection capabilities, emitted light when the universe was just 1/11 its current size, roughly 480 million years after the Big Bang. The universe was denser, hotter, and smaller by a factor of 11 in every dimension. Volume scales as the cube of distance, so the universe contained 11 cubed, or 1,331 times less volume than today. Yet that smaller universe already contained the matter that exists today. The same quantity of dark matter, normal matter, and dark energy filled a volume 1,331 times smaller. Density was correspondingly higher. Matter clumped more easily under gravity because particles didn't need to travel as far to encounter each other. This density advantage helped structure form quickly, offsetting the lack of time available for gravitational collapse. But even accounting for higher density, the massive galaxies James Webb observes remain difficult to explain. Computer simulations of structure formation, which track the gravitational interactions of billions of dark matter particles and gas clouds, rarely produce galaxies as massive as Webb detects at such early times. The simulations might be missing key physics. Perhaps the initial density variations were more extreme than assumed. Perhaps feedback processes that regulate star formation, like supernova explosions and radiation pressure from young stars, operated differently in the early universe. Perhaps dark matter halos collapsed more efficiently than models predict. Alternatively, the problem might lie with how we interpret the observations. Determining the mass of a distant galaxy requires measuring its light output and estimating the number and types of stars that produce that light. Young, massive stars shine brightly, dominating the light output of galaxies, undergoing intense star formation. If the early galaxies Webb observes contain an unusually high proportion of these massive stars, their total light output could be high, even if the total stellar mass is relatively modest. But spectroscopic observations, which analyze the detailed wavelengths of light from these galaxies, suggest they contain substantial stellar mass, not just a few bright, massive stars. The spectra show absorption lines from elements like carbon and oxygen, indicating multiple generations of stars have already enriched the gas. Building up significant heavy element abundances requires time and stellar mass. The galaxies Webb observes genuinely appear to be massive, not merely bright. This presents a fundamental challenge to cosmology. Our models of the universe's evolution must accommodate rapid structure formation, or we must revise our understanding of galaxy assembly. Either path has profound implications for what we think we know about cosmic scale and cosmic history. One approach to resolving this tension involves reconsidering the nature of dark matter. Standard models assume dark matter consists of collisionless particles that interact only through gravity. But if dark matter particles can interact with each other through additional forces, they might behave differently during structure formation. Self-interacting dark matter could dissipate energy through collisions, allowing dark matter halos to collapse more compactly and efficiently than non-interacting dark matter. This denser concentration of dark matter would create stronger gravitational wells, pulling in normal matter more rapidly and accelerating galaxy formation. Evidence for self-interacting dark matter comes from observations of galaxy cluster collisions. When two galaxy clusters merge, their dark matter halos pass through each other while the hot gas between galaxies collides and heats up, slowing down due to ram pressure. By comparing the positions of the dark matter halos, mapped through gravitational lensing, to the positions of the gas, astronomers can infer whether dark matter particles collide with each other. Some observations suggest slight offsets between dark matter and gas, hinting at dark matter self-interactions, but the evidence remains inconclusive. James Webb cannot directly observe dark matter, but it can measure the distribution of normal matter in distant galaxies with unprecedented precision. If dark matter self-interactions significantly affect structure formation, the galaxies Webb observes should show specific patterns in their density profiles and morphologies. Teams are analyzing Webb's data to search for these signatures, comparing observations to simulations with different dark matter models. Another possibility involves primordial black holes. If a significant fraction of dark matter consists of black holes formed in the early universe, these objects could serve as seeds for rapid galaxy formation. Gas falling into primordial black holes would heat up and emit radiation, triggering the collapse of nearby gas clouds into stars. The black holes themselves would merge, quickly building up the supermassive black holes that James Webb detects at cosmic dawn. Primordial black holes could form through several mechanisms. Density fluctuations during inflation might create regions so dense they immediately collapsed into black holes after inflation ended. Phase transitions in the early universe, moments when the vacuum state of space changed properties, could produce black holes as a byproduct. Cosmic strings, one-dimensional defects in space predicted by some theories of particle physics, could fragment and collapse into black holes. Detecting primordial black holes requires observing their gravitational effects. If they comprise a significant fraction of dark matter, they should gravitationally lens background stars and quasars, creating brief brightening events as a black hole passes in front of a more distant light source. Surveys searching for these micro-lensing events have placed constraints on the abundance of primordial black holes, ruling out the possibility that they comprise all of dark matter. But a smaller population of primordial black holes could still play a role in structure formation. James Webb's observations of supermassive black holes at cosmic dawn might provide indirect evidence for primordial black holes. If supermassive black holes grow from primordial seeds, they can reach millions of solar masses quickly by accreting surrounding gas and by merging with other black holes. This pathway avoids the problem of forming supermassive black holes from the collapse of individual massive stars, which takes much longer. But the scale of the universe revealed by James Webb extends beyond galaxies and black holes. The telescope has also observed the cosmic web itself, the vast network of filaments and voids that define large-scale structure. While previous surveys mapped this structure in the nearby universe, Webb reveals how the cosmic web appeared in the early universe when it was still assembling. The filaments contain most of the universe's galaxies, threaded like beads on strings of dark matter. The voids between filaments contain few galaxies, appearing as empty regions in three-dimensional maps of the universe. But the voids aren't truly empty. They contain dark matter, dark energy, and wisps of gas, just at much lower densities than the filaments. The contrast between filaments and voids defines the cosmic web's appearance, a foam-like structure with dense strands surrounding empty bubbles. James Webb can trace this structure back to when the universe was less than 1 billion years old. At those early times, the filaments were shorter and less well-defined. Galaxies clustered in small groups, rather than the elongated filaments seen today. Voids were smaller. The entire structure appeared more granular, like a foam that hasn't fully expanded. Over billions of years, cosmic expansion stretched the web. Filaments lengthened, voids grew larger. Galaxies within filaments merged and evolved. The granular structure visible in Webb's images of the early universe gradually transformed into the large-scale structure we observe in nearby space today. Mapped by surveys like the Sloan Digital Sky Survey. The scale of this structure is staggering. The largest filaments stretch for hundreds of millions of light-years. The largest voids span similar distances. The entire observable universe contains only a few thousand independent filaments and voids, meaning each structure represents a significant fraction of observable space. When we observe a void 200 million light-years across, we're looking at a region that comprises a sizable portion of the visible cosmos, a bubble of relative emptiness that represents one of the fundamental organizational units of cosmic structure. James Webb's deep field images capture multiple filaments at different distances, creating a layered view of cosmic structure across time. Galaxies in the foreground, relatively nearby at just a few billion light-years, appear large and detailed. Galaxies in the middle distance, 5 to 8 billion light-years away, appear smaller but still resolved. Galaxies in the background, more than 10 billion light-years distant, appear as faint smudges, their light redshifted and dimmed by distance and cosmic expansion. This layering reveals how cosmic structure has evolved. The foreground galaxies reside in well-defined filaments and clusters. The background galaxies show less organization, scattered more randomly across the sky. The transition between these regimes marks the epoch when the cosmic web became fully established, when gravitational attraction along filaments had pulled galaxies into coherent structures rather than leaving them distributed more uniformly. The timing of this transition, occurring roughly 8 to 10 billion years ago, corresponds to the era of peak star formation in the universe. Galaxies formed stars most rapidly when the universe was 2 to 4 billion years old, then gradually declined in star formation rate as gas supplies were exhausted and as cosmic expansion made it harder for gas to fall into galaxies. The cosmic web's assembly and the peak of star formation appear to be linked, both driven by the gravitational growth of structure during a critical epoch when the universe transitioned from youth to maturity. James Webb observes this transition in detail, capturing galaxies at every stage of evolution. Some galaxies appear young and irregular, filled with bright blue stars and lacking the spiral or elliptical morphologies of mature galaxies. Others appear fully formed, with clear spiral arms or smooth elliptical profiles. The diversity of galaxy types at every epoch suggests that galaxy evolution follows multiple pathways, not a single sequence from irregular to spiral to elliptical. This diversity complicates efforts to understand how galaxies form and evolve. Astronomers once thought galaxy evolution proceeded simply, with small, irregular galaxies merging to form larger spiral galaxies, which eventually merged into massive elliptical galaxies. But observations show that spiral galaxies can persist for billions of years without transforming into ellipticals. Some elliptical galaxies appear to form directly from the collapse of massive gas clouds rather than from mergers. Galaxy evolution is messier and more complex than early theories suggested. James Webb's observations add another layer of complexity. The massive galaxies at cosmic dawn don't fit neatly into evolutionary schemes. They appear too mature, too organized, too similar to modern galaxies for their age. Either galaxy evolution can proceed extremely rapidly under the right conditions, transforming chaotic gas clouds into structured galaxies in just a few 100 million years, or our understanding of what constitutes a young galaxy needs revision. Perhaps morphology doesn't directly indicate age. A galaxy can appear mature, with well-defined spiral arms or a smooth elliptical profile, even if it formed recently, provided the gas from which it formed was already rotating and structured. If the dark matter halo that hosts a galaxy is itself rotating and flattened, the gas falling into that halo will naturally form a disk, which can develop spiral structure quickly through gravitational instabilities. Alternatively, what appears as a single massive galaxy in James Webb's images might actually be multiple smaller galaxies in the process of merging, their light blending together due to the telescope's limited resolution at extreme distances. Future observations with even more powerful instruments might resolve these apparently massive galaxies into clusters of smaller objects, alleviating the tension with theoretical models. But the scale problem remains. Even if individual galaxies are smaller than they appear, the sheer number of galaxies Webb detects at cosmic dawn exceeds predictions. The universe formed stars and assembled galaxies more efficiently than simulations suggest. The volume of space that participated in early structure formation was larger than expected. More of the universe's matter concentrated into galaxies at early times, leaving less material in the diffuse intergalactic medium. This efficient conversion of gas into stars has implications for the chemical evolution of the universe. Every star that forms locks up matter in stellar form, removing it from the gas that could form future generations of stars. If the early universe formed stars very efficiently, it should have depleted its gas supply quickly, leading to a decline in star formation rates earlier than observed. But star formation hasn't declined as rapidly as efficient early star formation would predict. The universe continues to form stars today, roughly 13.8 billion years after the Big Bang, at a rate of about 1 solar mass per year, per cubic megaparsec of volume. That's low compared to the peak star formation rate 10 billion years ago, but it's not zero. Gas supplies haven't been completely exhausted. Something replenishes the gas or prevents it from being entirely converted into stars. The answer involves feedback processes. When massive stars explode as supernova, they inject energy into the surrounding gas, heating it and driving powerful winds that can blow gas out of galaxies entirely. This negative feedback reduces star formation by removing the raw material from which stars form. But supernovae also compress gas in some regions, triggering new bursts of star formation in a positive feedback loop. The balance between positive and negative feedback determines how efficiently galaxies convert gas into stars. James Webb can observe these feedback processes in action by imaging galaxies undergoing intense star formation. The telescope detects the infrared glow of dust heated by young stars and the emission lines from ionized gas in star-forming regions. It also observes galaxies where star formation has been quenched, their gas supplies exhausted or blown away, leaving behind populations of older red stars. The transition from star forming to quenched represents a critical phase in galaxy evolution. Understanding what triggers this transition helps explain why some galaxies continue forming stars for billions of years, while others stop abruptly. Possible causes include gas depletion, supernova feedback, and interactions with other galaxies. Supermassive black holes at galaxy centers might also play a role, heating or ejecting gas through powerful jets, and winds driven by matter falling into the black hole. James Webb's observations reveal that quenching can occur very early in cosmic history. Some galaxies at redshift Z equals 3 or 4, corresponding to when the universe was 2 to 3 billion years old, show signs of quenching. These galaxies formed stars intensely for a few 100 million years, then stopped. Their stellar populations aged, turning red as the bright blue massive stars died, leaving behind longer-lived red dwarfs and evolved red giants. The existence of quenched galaxies at such early times suggests that feedback processes operated efficiently even in the young universe. Supermassive black holes had already grown to masses where their energy output could affect their host galaxies. Supernova rates were high enough to drive significant gas outflows. The mechanisms that regulate star formation today were already active billions of years ago, shaping galaxy evolution from nearly the beginning. This early regulation of star formation connects to the question of cosmic scale, because it determines how matter is distributed across the universe. In a scenario where star formation proceeds unchecked, most matter would be locked up in stars and black holes, with little gas remaining in the intergalactic medium. In a scenario with strong feedback, significant gas remains outside galaxies, filling the cosmic web's filaments and even the voids with diffuse material that might eventually fall into galaxies and form future generations of stars. Observations suggest the latter scenario is closer to reality. The intergalactic medium contains roughly as much normal matter as galaxies themselves. This gas is hot, heated to millions of degrees by shock waves from structure formation and by radiation from galaxies and quasars. It emits X-rays, which can be detected by X-ray telescopes, and it absorbs ultraviolet light from background quasars, creating absorption lines that reveal the gas's presence and properties. James Webb cannot observe X-rays, but it can detect the effects of hot gas on the formation and evolution of galaxies. Galaxies falling into massive galaxy clusters must pass through this hot intra-cluster medium, which strips away the galaxy's gas through ram pressure, a process similar to feeling wind resistance while moving quickly through air. This stripping quenches star formation, transforming gas-rich spiral galaxies into gas-poor ellipticals as they plunge into the cluster environment. The scale of these environmental effects reaches beyond individual galaxies to encompass entire clusters and superclusters, regions containing thousands of galaxies spread across tens of millions of light-years. The environment determines a galaxy's fate, whether it continues forming stars or becomes quenched, whether it retains a spiral structure or transforms into an elliptical. The cosmic web's architecture influences galaxy evolution across vast volumes of space, coupling the fates of galaxies separated by millions of light-years through the effects of large-scale structure. James Webb's wide field of view allows it to observe these environmental effects directly. The telescope can image entire galaxy clusters, capturing hundreds of galaxies in a single frame, and revealing how galaxy properties vary with position in the cluster. Galaxies near the cluster center tend to be red and quenched. Galaxies in the outskirts are more often blue and star-forming. The transition between these regimes occurs at specific radii, marking where the environmental effects become strong enough to shut down star formation. By observing clusters at different distances, corresponding to different epochs in cosmic history, Webb reveals how environmental effects have evolved over time. Clusters in the early universe show less dramatic environmental effects. Galaxies retain their gas and continue forming stars even near cluster centers. As the universe ages and clusters mature, the intracluster medium heats up and becomes denser, making environmental effects more powerful and transforming cluster galaxies more efficiently. This evolution of cluster environments contributes to the overall decline in cosmic star formation rate. Early in the universe's history, most galaxies resided in relatively low-density environments where gas remained plentiful and star formation continued unabated. As structure formed and clusters assembled, an increasing fraction of galaxies found themselves in hostile, high-density environments where gas stripping quenched star formation. The cosmic star formation rate declined, not only because individual galaxies exhausted their gas supplies, but because galaxies increasingly ended up in environments that prevented star formation. The scale of this process encompasses the entire observable universe. Every galaxy's evolution is influenced by its environment, which in turn is determined by its position in the cosmic web. The web's structure reaches back to the initial density fluctuations in the early universe, quantum jitters during inflation that were amplified by cosmic expansion and shaped by gravity over billions of years. The galaxy you observe today, whether star-forming or quenched, spiral or elliptical, isolated or in a cluster, reflects the properties of the region of space where it formed and the history of that region's evolution over cosmic time. James Webb makes this connection visible by observing the same region of sky at multiple wavelengths. Infrared light reveals different properties of galaxies than visible light. Short wavelength infrared traces hot stars and active star formation. Long wavelength infrared penetrates dust, revealing regions hidden at visible wavelengths. By combining images at different wavelengths, astronomers construct complete pictures of galaxy properties, measuring stellar masses, star formation rates, dust content, and gas supplies. These multi-wavelength observations reveal that galaxies are complex systems with multiple components, each contributing to the total light output and each telling part of the story of the galaxy's formation and evolution. The stellar disk contains most of the galaxy's stars, arranged in spiral arms in spiral galaxies or in a smooth distribution in ellipticals. The bulge, a central concentration of stars, contains older stellar populations and often hosts the supermassive black hole. The halo, extending far beyond the visible galaxy, contains dark matter and populations of old stars in globular clusters. Each component formed at different times and through different processes. The halo formed first, as dark matter collapsed under gravity. The disk formed later, as gas fell into the gravitational well created by the dark matter halo and settled into a rotating plane. The bulge formed through gas inflows to the galaxy center, or through mergers of smaller galaxies. The supermassive black hole grew through accretion of gas and through mergers with other black holes. James Webb observes galaxies at stages where these components are still assembling. Some early galaxies lack clear bulges, appearing as pure disks. Others show irregular morphologies suggesting ongoing mergers. A few already possess massive bulges and show signs of mature structure. The diversity indicates that galaxy assembly doesn't follow a single timeline. Different galaxies in different environments form their components in different orders and at different rates. This diversity complicates efforts to measure cosmic scale through galaxy surveys. Astronomers use galaxies as tracers of large-scale structure, mapping their positions in three-dimensional space to reveal the cosmic web. But if different types of galaxies form in different environments, then surveys that select only certain types might miss important aspects of the web's structure. Blue star-forming galaxies might trace filaments well, but miss voids. Red quenched galaxies might concentrate in clusters, accurately mapping those dense regions, but providing less information about the broader web. James Webb's ability to detect galaxies of all types at all epochs helps address this bias. The telescope's deep infrared sensitivity allows it to detect both bright, star-forming galaxies and faint, quenched galaxies at cosmic dawn. By observing complete samples of galaxies rather than biased subsets, Webb provides a more accurate picture of how structure formed and evolved. That picture reveals a universe that is more structured, more organized, and more complex than we imagined before James Webb began observations. The scale of structure extends further back in time. Massive galaxies appear earlier. The cosmic web assembles faster. Environmental effects operate sooner. The universe wasted little time transitioning from the smooth, nearly uniform state revealed by the cosmic microwave background to the richly structured cosmos we observe today. But the smooth cosmic microwave background itself hides complexities. While the average temperature is 2.725 Kelvin across the sky, tiny variations at the level of 100 microkelvins encode information about conditions in the early universe. These temperature fluctuations correspond to density variations, regions slightly denser or less dense than average at the time the cosmic microwave background formed. The statistical properties of these fluctuations reveal fundamental aspects of cosmic structure. The typical angular size of hot and cold spots, roughly 1 degree on the sky, corresponds to the distance sound waves could travel in the plasma before atoms formed and sound propagation stopped. This characteristic scale, called the sound horizon, depends on the density of matter, the density of dark energy, and the curvature of space. Measuring it provides constraints on cosmological parameters. The amplitude of the fluctuations, how much they differ from the average temperature, depends on the density of matter and on the initial conditions during inflation. Larger initial fluctuations produce larger temperature variations in the cosmic microwave background and faster structure formation in later epochs. The observed amplitude, roughly 20 parts per million at the largest scales, indicates that the initial density fluctuations from inflation were small, just enough to seed structure formation, but not so large as to create premature collapse into black holes. James Webb's observations of rapid structure formation suggest the need to revisit these interpretations. If massive galaxies form earlier than the cosmic microwave background fluctuations predict, either the fluctuations were larger than measured, perhaps including components invisible to microwave observations, or structure formation proceeds more efficiently than simulations show, with gravity pulling matter together faster than standard physics allows. Neither possibility fits comfortably within established cosmology. The cosmic microwave background is one of the most precisely measured phenomena in all of science. The Planck satellite's observations determined cosmological parameters to percent-level precision, creating a standard model of cosmology that fits a wide range of independent observations. Revising the interpretation of the cosmic microwave background to accommodate James Webb's observations would require finding flaws in that precise measurement or in the theoretical framework that connects microwave temperature fluctuations to density variations. The alternative, that gravity operates differently than we understand, threatens the foundation of cosmology even more directly. General relativity, Einstein's theory of gravity, has passed every experimental test over more than a century. It correctly predicts the precession of Mercury's orbit, the bending of light by the sun, the gravitational redshift of light escaping massive objects, and the existence of black holes. It forms the basis for cosmology, describing how the universe expands, how structure forms, and how space itself curves in response to matter and energy. Modifications to general relativity have been proposed to address various puzzles in cosmology and astrophysics. Some modifications attempt to explain the rotation curves of galaxies without invoking dark matter. Others try to account for cosmic acceleration without dark energy. A few propose changes to how gravity operates on cosmological scales, altering the growth rate of structure formation. James Webb's observations might provide evidence for or against these modified gravity theories. If structure forms faster than general relativity predicts, even after accounting for all known forms of matter and energy, that discrepancy could indicate new physics in gravity. But the evidence must be compelling, requiring detailed comparisons between observations and simulations, careful accounting for uncertainties, and independent confirmation from multiple sources. For now, the tension between James Webb's observations and theoretical predictions remains unresolved. Astronomers continue to analyze Webb's data, refining measurements of galaxy masses, ages, and star formation rates. Theorists run new simulations with different initial conditions, different dark matter models, and different feedback prescriptions, searching for combinations that reproduce the observations. The process is ongoing, with new papers appearing monthly as the community wrestles with the implications of what James Webb has revealed. The scale of the effort matches the scale of the discovery. Hundreds of astronomers across dozens of institutions collaborate on James Webb programs, sharing data and coordinating observations. Thousands of CPU hours on supercomputers are devoted to simulations. Terabytes of data flow from the telescope to archives, and from archives to researchers around the world. The investigation of cosmic scale has itself become a large-scale enterprise, requiring coordination and resources comparable to the construction of the telescope itself. This collective effort reflects the importance of the questions James Webb addresses. Understanding cosmic scale means understanding the universe's size, its age, its contents, and its evolution. These questions connect to deeper issues about existence, about why there is something rather than nothing, about whether the universe is finite or infinite, about our place in the cosmic hierarchy. James Webb cannot answer these ultimate questions directly, but it provides data that constrains possible answers. An infinite universe filled with infinite matter requires different explanations than a finite universe of limited size and content. A universe that forms structure rapidly differs from one where structure emerges slowly through gradual gravitational collapse. The details matter. They determine what kinds of universes are possible, what kinds of physics operate on cosmic scales, and what kinds of futures the cosmos might have. Consider the implications of rapid structure formation for the universe's ultimate fate. If gravity efficiently pulls matter together into galaxies and clusters, those structures become gravitationally bound, isolated from cosmic expansion. The expansion of space continues, but bound structures don't expand with it. Galaxies don't grow larger. Clusters don't disperse. The matter within these structures remains concentrated, resisting the tendency of expansion to dilute everything. Over trillions of years, cosmic expansion will carry most galaxies beyond the cosmic horizon, the distance beyond which light cannot reach us because space expands faster than light travels. The observable universe will shrink, containing only the Milky Way and the galaxies gravitationally bound to it in the local group, a collection of about 50 galaxies spanning 10 million light-years. All other galaxies will have receded beyond the horizon, their light stretched to infinite wavelengths, effectively becoming invisible. But the local group will remain intact. Gravity overcomes cosmic expansion on these scales. The galaxies within the local group will continue to interact, orbit, and eventually merge. The Milky Way is already on a collision course with the Andromeda Galaxy, approaching at 110 kilometers per second and due to merge in roughly 4.5 billion years. The collision will disrupt both galaxies, ejecting some stars into intergalactic space and funneling gas toward the centers, where it will trigger intense star formation before the gas is exhausted. The result will be a giant elliptical galaxy, sometimes called Milkomeda, containing all the stars from both progenitors. Other galaxies in the local group will eventually merge with this central elliptical, creating an even larger structure. Trillions of years in the future, the local group will have coalesced into a single massive elliptical galaxy, containing all the stars from the original member galaxies. This remnant will float alone in an expanding universe, with all other galaxies having receded beyond the horizon. The stars in this ultimate galaxy will gradually age and die. Massive stars will explode as supernovae or collapse into black holes. Sun-like stars will expand into red giants and shed their outer layers, leaving behind white dwarfs. Red dwarfs, the smallest and longest-lived stars, will continue fusing hydrogen for trillions of years, outlasting all other stellar types. Eventually, even red dwarfs will exhaust their fuel, cooling into black dwarfs, stellar remnants that emit no light. The ultimate galaxy will fade, growing darker as its stars die and no new stars form to replace them. Gas supplies will have been exhausted long before, locked up in stellar remnants or ejected from the galaxy by ancient supernovae. Without gas, no new stars can form. The galaxy will contain only dead stellar remnants, white dwarfs, neutron stars, and black holes orbiting in a dark gravitational dance. Trillions of years will pass. The stellar remnants will gradually spiral inward, losing energy to gravitational wave radiation as they orbit. Eventually, they will merge, forming larger black holes. The process continues until most of the galaxy's mass has coalesced into a single supermassive black hole at the center, with a scattering of smaller black holes and stellar remnants in distant orbits around it. Black holes themselves are not eternal. Stephen Hawking showed that black holes emit radiation through quantum effects at their event horizons, a process now called Hawking radiation. This radiation causes black holes to lose mass extremely slowly, evaporating over timescales that make the current age of the universe seem like an eye blink. A black hole with the mass of the Sun would take 10 to the 67th power years to evaporate completely. A supermassive black hole containing billions of solar masses would take 10 to the 100th power years or longer. But even these incomprehensible timescales eventually pass. In the unimaginably distant future, all black holes will have evaporated. The universe will contain only photons, neutrinos, and other stable particles, spread across vast distances by cosmic expansion, growing ever colder as the universe continues to expand and cool. The temperature will approach absolute zero. The energy density will approach zero. The universe will enter a state sometimes called heat death, a condition of maximum entropy where no gradients exist, no work can be done, and nothing changes. This ultimate fate seems bleak, the end of all structure, all complexity, all life. But it's predicated on specific assumptions about the laws of physics, the nature of dark energy, and the stability of matter. If any of these assumptions is wrong, the fate of the universe might differ dramatically. If dark energy increases in strength over time, rather than remaining constant, cosmic expansion could accelerate so much that it tears apart even gravitationally bound structures. This scenario, called the Big Rip, would occur on much shorter timescales than heat death, potentially in as little as 20 billion years. Galaxy clusters would be torn apart first, then galaxies, then stellar systems, then planets, then atoms themselves as the expansion of space overcomes all fundamental forces. If dark energy decreases or reverses, cosmic expansion could slow, stop, and reverse, pulling the universe into a big crunch, the opposite of the Big Bang. All matter and energy would collapse toward a single point, increasing in density and temperature until the universe reaches a state similar to the moment just after the Big Bang, a hot, dense plasma where the laws of physics, as we know them, break down. Some theories propose that the Big Crunch could bounce, triggering a new Big Bang and beginning a new cycle of expansion and contraction. These cyclic models imagine an eternal universe that oscillates between Big Bangs and Big Crunches, with each cycle potentially producing different laws of physics, different constants of nature, and different outcomes for structure formation. James Webb cannot observe the far future to determine which fate awaits the universe, but it can measure properties of dark energy by observing how cosmic expansion has evolved over time. By detecting galaxies at many different distances, Webb maps the expansion history of the universe. Comparing the observed expansion history to theoretical predictions constrains the properties of dark energy, determining whether it remains constant, increases, or decreases over time. Current observations suggest dark energy is consistent with a cosmological constant, a form of energy with constant density even as the universe expands. This constancy implies that dark energy's influence grows over time as matter and radiation dilute. The universe's expansion accelerates. The ultimate fate approaches heat death, not the Big Rip or Big Crunch. But the measurements remain uncertain enough that alternatives cannot be ruled out completely. Future observations, including continued monitoring by James Webb and upcoming surveys by next-generation telescopes, will refine our understanding of dark energy and narrow the possibilities for the universe's fate. Whatever that fate may be, the scale of time involved dwarfs the scale of space. The universe is currently 13.8 billion years old. Heat death lies 10 to the 100th power years in the future. The ratio between these timescales is incomprehensible, a number with 100 zeros. We exist in the first instant of cosmic history, the brief moment when stars shine, galaxies exist, and complexity flourishes. the vast expanse of cosmic future will be dark, cold and empty, dominated by expansion and entropy. Yet within this brief flourishing moment, the universe has accomplished extraordinary things. It has assembled matter into stars and galaxies. It has synthesized heavy elements in stellar furnaces. It has allowed planets to form, atmospheres to develop, and on at least one planet, life to emerge. Life has evolved into conscious beings capable of observing the universe, measuring its properties, and contemplating its fate. This emergence of consciousness from unconscious matter represents one of the universe's most remarkable achievements. Atoms forged in stellar cores combined into molecules, molecules organized into cells, cells cooperated into multicellular organisms. Organisms developed nervous systems, brains, and eventually self-awareness. The process took billions of years on Earth and required specific conditions: liquid water, stable energy sources, a protective atmosphere, and sufficient time for evolution to explore the vast space of possible biological forms. The scale of this evolutionary process is as impressive as the scale of cosmic structure formation. Both represent the universe organizing itself, creating complex patterns from simple initial conditions, building elaborate structures through the operation of physical laws over long time periods. Stars assemble from clouds of hydrogen and helium. Galaxies assemble from stars. Life assembles from atoms. Consciousness emerges from life. James Webb observes the cosmic side of this story, mapping how stars and galaxies form. Understanding biological emergence requires different tools: telescopes that can observe the atmospheres of distant planets, searching for biosignatures like oxygen and methane that might indicate the presence of life. Future telescopes like the Habitable Worlds Observatory might detect such signatures, revealing whether life is common or rare in the universe. If life is common, the universe might be teeming with living worlds, scattered across billions of galaxies, each following its own evolutionary path, producing its own forms and perhaps its own versions of intelligence and consciousness. If life is rare, Earth might be one of few oases in a largely barren cosmos, making the consciousness that evolved here precious beyond measure. James Webb's observations of rapid structure formation and early chemical enrichment suggest conditions favorable for life emerged quickly across large volumes of space. If heavy elements appeared when the universe was just a few 100 million years old, and if those elements distributed themselves into gas clouds that eventually formed stars and planets, then the building blocks for life became available early in cosmic history. Planets capable of hosting life might have existed when the universe was just 1 billion years old, more than 12 billion years ago. If life emerges quickly on favorable planets, and if a small fraction of life develops intelligence and technology, the universe could have hosted technological civilizations for more than 10 billion years. The silence of the cosmos, the absence of any detected signals or artifacts from these hypothetical civilizations, suggests either that life is rare, that intelligence is rare, that technology is rare, or that technological civilizations don't last long enough to make their presence known across interstellar or intergalactic distances. The scale of time and space involved makes communication between civilizations difficult, even if many exist. Radio signals travel at the speed of light, taking thousands or millions of years to cross the distances between stars. A signal sent from a civilization 10,000 light-years away would take 10,000 years to reach us. Our reply would take another 10,000 years to return. The round-trip conversation time exceeds the lifespan of most civilizations if they face the same existential risks that human civilization confronts: climate change, nuclear war, resource depletion, asteroid impacts, or other threats. The expansion of the universe makes communication even harder for civilizations separated by cosmological distances. Galaxies billions of light-years away recede from us faster than light can travel, carried by the expansion of space itself. Signals sent towards such galaxies will never arrive. The light will be redshifted to infinite wavelengths, stretched by expansion until it becomes undetectable. Any civilizations in those distant galaxies remain forever beyond our ability to contact, separated not merely by distance but by the expanding geometry of space-time itself. This isolation is both profound and perhaps inevitable given cosmic scale. The universe is large enough that vast numbers of habitable worlds likely exist, but also so large that communication between worlds becomes nearly impossible, except for nearest neighbors. Each civilization develops in isolation, wondering if others exist but unable to confirm or contact them. James Webb looks backward in time, observing light from the early universe, but it cannot tell us whether life exists elsewhere. It can only measure the conditions, the abundance of heavy elements, the formation of planets, the environments around stars that might permit life to develop. Future telescopes will search more directly for biosignatures, but the search will be limited to nearby stars within a few dozen or at most a few hundred light-years, a tiny bubble within the Milky Way, itself just one of 2 trillion galaxies in the observable universe. The scale of what we can observe in detail is minute compared to the scale of the cosmos. James Webb can detect galaxies 13 billion light-years away, but it sees them as faint smudges, tiny collections of photons carrying minimal information. Detailed observations remain limited to relatively nearby objects. We can map cosmic structure across billions of light-years, but we understand individual galaxies only out to tens or hundreds of millions of light-years. We can detect exoplanets around nearby stars, but we can characterize their atmospheres only for the nearest examples, those within a few dozen light-years. This observational horizon constantly expands as technology improves. Telescopes grow larger. Detectors become more sensitive. Techniques develop for extracting more information from limited data. James Webb represents the current frontier of this expansion, but future telescopes will push further, observing fainter objects, collecting more detailed spectra, and mapping structure across larger volumes of space and further back in time. Yet there are fundamental limits. The cosmic horizon set by the finite age of the universe and the finite speed of light cannot be overcome. No observation can reveal what lies beyond the observable universe. If the universe is infinite, most of it remains forever beyond our reach. If the universe is finite but larger than the observable portion, we cannot observe the distant regions from which light hasn't yet had time to reach us. These limits mean that certain questions about cosmic scale may remain unanswerable. Is the universe finite or infinite? If finite, what is its total size? What lies beyond the cosmic horizon? Are the laws of physics the same everywhere, or do they vary in distant regions? Do other universes exist, separated from ours by dimensions we cannot access or by barriers we cannot penetrate? James Webb cannot answer these ultimate questions, but it reveals how much we have learned and how much remains unknown. The telescope's observations of the early universe, of rapid structure formation, of massive galaxies and supermassive black holes at cosmic dawn, demonstrate that the universe is more complex and more surprising than our models predicted. The scale of cosmic structure, the efficiency of galaxy formation, and the speed at which the universe organized itself all exceeded expectations. These surprises don't overturn cosmology. They refine it, adding detail and complexity to our understanding, revealing aspects of cosmic evolution we hadn't appreciated. The process of science involves comparing predictions to observations, adjusting models when they disagree, and gradually converging on more accurate descriptions of reality. James Webb participates in this process, providing data that challenges assumptions and forces reconsideration of established ideas. The telescope doesn't prove existing models wrong. It shows where they're incomplete, where additional physics might be needed, where our understanding remains uncertain. The massive galaxies at cosmic dawn don't disprove the Big Bang or overturn general relativity. They suggest that structure formation involves processes we haven't fully characterized, that dark matter might interact in ways we haven't measured, or that the initial conditions in the early universe differed from what we inferred from the cosmic microwave background. Resolving these tensions will take years of additional observations, simulations, and theoretical work. The process has already begun. Astronomers are analyzing James Webb's data in detail, measuring properties of distant galaxies with increasing precision. Theorists are exploring new models, testing whether modified dark matter physics or different feedback processes can reproduce the observations. Simulators are running massive computations, tracking the evolution of billions of particles over cosmic time, comparing the resulting virtual universes to what James Webb observes in the real universe. This collaborative effort spans the globe. Researchers in dozens of countries contribute to understanding James Webb's discoveries. Data is shared through international archives. Papers are published in journals read worldwide. Conferences bring together scientists to discuss findings and debate interpretations. The investigation of cosmic scale is itself a global undertaking, reflecting humanity's collective effort to understand its place in the universe. That place is both smaller and larger than we might think. Smaller because the universe is vast beyond comprehension, containing structures that dwarf human scales by factors of trillions or more. A human being, roughly 2 meters tall, compares to the observable universe, roughly 10 to the 26th power meters in diameter, as an atom compares to the distance between Earth and the Sun. We are infinitesimally small, occupying a tiny planet around an ordinary star in an unremarkable galaxy among trillions of others. Yet we are also larger than our physical size suggests. We are made of atoms forged in stellar cores, the products of nuclear fusion in stars that exploded billions of years ago. The carbon, oxygen, nitrogen, and other elements in our bodies were synthesized through nucleosynthesis, scattered into space by supernovae, and incorporated into the molecular cloud that eventually collapsed to form the solar system. We are literally made of stardust, our bodies composed of matter, processed through multiple stellar generations. Moreover, we possess consciousness, the ability to observe the universe, to contemplate its properties, to formulate theories and test them against reality. This capacity for understanding connects us to the cosmos in profound ways. When we observe a distant galaxy through James Webb's images, we are seeing across billions of light years, our minds reaching through space and time to comprehend structures vastly larger and older than ourselves. The universe has become aware of itself through conscious observers, matter organized into patterns complex enough to reflect on their own existence. This reflection raises philosophical questions that science alone cannot answer. Why does the universe exist? Why does it follow mathematical laws? Why is it comprehensible to conscious minds? These questions lie at the boundary between science and philosophy, where empirical observation meets metaphysical speculation. James Webb doesn't address these questions directly, but its observations inform them. A universe that rapidly forms structure, that efficiently synthesizes heavy elements, that creates conditions favorable for complexity, suggests a cosmos predisposed toward organization rather than chaos. Whether this predisposition reflects fundamental properties of physical law, anthropic selection among many possible universes, or something else entirely remains open to debate. What James Webb reveals with certainty is the scale, the sheer magnitude of the universe in space, in time, in structure, and in complexity. The 93 billion light-years of the observable universe, the 13.8 billion years since the Big Bang, the 2 trillion galaxies, the hundreds of billions of trillions of stars, the impossible early formation of massive galaxies and black holes, all point to a cosmos larger, older, and more complex than humans could have imagined mere centuries ago. Yet, we have imagined it. Through mathematics and physics, through observations and reasoning, we have mapped the cosmos across scales that exceed direct experience by factors of 10 to the 26th power in distance and 10 to the 17th power in time. We have inferred the existence of dark matter and dark energy, components that comprise 95% of the universe, yet remain invisible to our instruments. We have traced cosmic history backward to fractions of a second after the Big Bang, and forward to the ultimate fate trillions of years hence. James Webb continues this project of cosmic mapping and understanding. Each image the telescope captures adds detail to our picture of the universe. Each spectrum reveals chemical compositions and physical conditions in distant galaxies. Each discovery raises new questions and opens new avenues of investigation. The process of science never truly ends. Each answer generates new questions. Each observation reveals new phenomena requiring explanation. The scale of what remains unknown likely exceeds the scale of what we have learned. The universe may be infinite, in which case, the fraction of it we have observed approaches zero. Even if finite, the universe extends far beyond the cosmic horizon, with most of its volume forever beyond our observational reach. The nature of dark matter and dark energy remains mysterious despite decades of research. The ultimate fate of the universe remains uncertain. The question of life elsewhere remains unanswered, yet the progress is real and remarkable. Humans have existed for hundreds of thousands of years, but scientific cosmology is barely a century old. Edwin Hubble discovered cosmic expansion in 1929. The cosmic microwave background was detected in 1965. Dark energy was discovered in 1998. James Webb launched in 2021. Within a single human lifetime, our understanding of the universe has been revolutionized multiple times. The pace of discovery continues to accelerate. James Webb will operate for decades, observing distant galaxies, characterizing exoplanet atmospheres, and mapping cosmic structure. Future telescopes will push even further with larger mirrors, more sensitive detectors, and innovative techniques. Ground-based observatories like the extremely large telescope, with its 39-meter primary mirror, will achieve unprecedented resolution. Space missions will search for Earth-like planets and biosignatures. Gravitational wave observatories will detect colliding black holes across cosmic distances. Neutrino telescopes will observe the universe through these weakly interacting particles. Each new instrument will reveal new aspects of cosmic scale and structure. The universe will continue to surprise us, challenging our models and expanding our understanding. The journey of discovery extends indefinitely into the future, limited only by the resources we devote to it and by the fundamental constraints imposed by physics. But for now, in this moment, James Webb has shown us how impossibly large the universe truly is. Not merely in distance or in time, but in its capacity for structure, for complexity, for rapid organization of matter into galaxies and stars. The telescope has revealed a cosmos that wastes no time, that leaps immediately into large-scale architecture, that produces massive structures while still young. This precocious universe, Forming galaxies when it should still be simple, assembling black holes when it should still be pristine, challenges us to reconsider what we thought we knew about cosmic evolution. The numbers remain staggering. 93 billion light-years in diameter, 2 trillion galaxies, hundreds of billions of trillions of stars, massive galaxies at cosmic dawn, supermassive black holes 300 million years after the Big Bang. Structure formation proceeding faster than simulations predict. A cosmic web already assembling when the universe was barely a billion years old. These observations don't make the universe larger in the sense of adding light years to its diameter. They make it larger in scope, in complexity, in the sheer amount of activity and structure formation occurring across its volume. The universe is more active, more dynamic, more efficiently organized than we realized. The scale of what the cosmos can accomplish in limited time exceeds our expectations. And beyond the observable universe lies more, perhaps infinitely more, space, continuing outward in all directions, containing more galaxies, more stars, more structure. Whether that space is finite or infinite, whether it curves back on itself or extends forever, whether it connects to other universes or exists alone, we cannot yet determine. The observations provide clues but not definitive answers. What we can say with confidence is that the universe revealed by James Webb is larger, more complex, and more mysterious than the universe we thought we understood before the telescope began operations. Each discovery adds to the scale, both literally in terms of measuring larger structures at greater distances, and figuratively in terms of expanding what we know is possible within cosmic evolution. If this journey through cosmic scale has resonated with you, consider that we've barely begun to explore what James Webb might reveal in the years ahead. The telescope will continue observing, capturing deeper images, studying more distant galaxies, and characterizing the universe across wavelengths invisible to human eyes. Each new observation carries the potential for discovery, for revealing phenomena we haven't yet imagined. Leave a like if you found wonder in the impossible scale of cosmic structure, in galaxies that formed too early, in a universe that organized itself too quickly, in the sheer magnitude of space and time that James Webb has brought into focus. And until next time, wherever and whenever you are in this vast, impossibly large universe, keep looking up, keep wondering, and keep reaching toward understanding.